Is a bit broken, but I believe that we have started. Okay, let's just get this all up. And Firefox is crashing again. You know, Firefox can do that if it wants to. Sometimes we're just like that, you know? We're just not in a working mood. Okay. We're going to type this in manually. Oh, okay, that is already there. It's been saved. That's good. It shouldn't be doing that. All right, where exactly are we? Working with environment variables? I believe we've already gone through that. We are at a quiz currently. Yes, right here. That's where we ended up at. Okay, let's pop out chat. Let's do this. That was the quickest I've ever done it. I'm proud of myself. I'm gonna pat myself on the back. Metaphorically. I don't have the wherewithal to do that. Okay, here's the YouTube chat. I like the YouTube chat. It can stay small though. Hey Sorbet, glad to see you again. Welcome in. Got this all working real quick. Well, I got the stream working. As you can see, not much else is working. Now YouTube's screaming at me. Hello. Right, so we are going to start with the quiz today, but I'm first going to CD into the correct area to get what is it called? Rust for Lemmings. Yes, that's what we're doing. We're doing that, and we're also, well, actually, I don't think we're actually doing anything specific, so I'll just clear this out. Hey. All right, glad to see you here again. Just going to say that once more for posterity and to distract you as I do other things on a different screen, you know? Maybe you won't notice that I've stopped completely. Okay. I think we're all ready to go. Let's see what we remember from the last time. And by we, I mean you, because I've forgotten it all. Right, we're going to jump right into the hard-hitting questions. No rest for us, my friend. Determine whether the program will pass the compiler. If it passes, write the expected output of the program if it were executed. I'm not going to stop like a train. Function, main, let mutable s equal string from hello, let mutable add suffix equal a closure, with nothing being brought in, which does s.push string. Taking in s, I believe this consumes ownership of it? Yes, this consumes ownership of it because strings cannot do not implement the copy trait. So because we are currently attempting to mutate this with a function on add suffix s, the ownership is kept with this. So print line s will not work because ownership does not end until the end, until the last use of this closure. So this will not compile. I think that's about reasonable. Just going to reread this again a little bit to make sure. To restate, I believe the reason why this will not compile is due to the fact that s is a string. String does not have copy. This is essentially a function. We are passing ownership over to this function. When it is created, it is then used. S is then attempted to be used, but it does not have ownership. It does, well, perhaps it has read. It doesn't have ownership, so it can't be mutated, but can it read? I don't see why it couldn't read. You know what? I've changed my mind very quickly. Because I'm not an intelligent creature. I'm just going to say it's going to say hello. I think it'll compile. I have faith in the Rust compiler to know that this is not unsafe. If you got any idea, I'm glad to hear it, but I'm just gonna go with this, honestly. Hello. Sorry to jump right in. I assume that you're not right at the computer right now. Still, though, excellent to see you. Glad to jump in. I probably should have done this last time. Can't remember why I jumped off. Right, this is the same idea. Hello, can you stop being selected? Thank you. Determine whether it runs and if it passes the. Sorry. And if it does, shout it out. Alright, so what we have here is immutable s is a hello string. We have add suffix, which is a function taking in a parameter of a reference to a mutable string. This borrows s.push string world. Puts world at the end of s, which is a borrowed reference. And we print it. This I don't think will compile. Maybe it will, honestly. To be honest, I see no reason why this wouldn't compile. I think I completely forgot about closures and ownership, to be entirely honest. I do think this will compile, but I don't like the idea that both these in a row were something that I believe will compile. String doesn't have copy traits, so passing it in like this takes away ownership, but I don't think that that takes away the read permission. I don't see why you wouldn't be able to read. Yeah, I think it will compile again as well. And it'll just output hello. Alright. Which of the following function traits is most appropriate to fit the blank? Oh god. Right. For every mutable. Meaning it can't, well, fn once is something that everything has. Right. For each mutable. Extracts a function with a mutable reference to each element of a vector. Executes a function with a mutable reference to each element of a vector. Okay. So what we're doing is we're passing in a closure, and it's running that on every piece of a vector. It brings in two things, I assume. Yep. The mutable function, or the mutable closure of any type, as long as it's static with f, and a mutable reference to a vector. Okay. We have mutable t, a reference to mutable t. I don't know what that is again. That's what I want to say too. I forgot too. My mind is blank. I can't remember what FN is. I believe that's there to trick us. I believe that's a false herring. I believe that's a purple herring or whatever they say. I'm also going to say FN mute because I see the word mute here. Also separately, I believe that FN once is the basic level, but FN mute can be utilized when it can be run more than once and has mutable output, different output depending on what's input. I believe FN mute's correct. Oh, what's this one? Consider the following API. We have a struct analyzer post-process, a function that takes a mutable reference of type T. Oh, well then, I believe that worked. I believe that works, right? No, I don't think that works then. Ooh, I think we may have gotten that wrong then, because it took in a reference vector. It wasn't a reference of type T. Huh. Well, I guess we'll learn. Right? What is the most appropriate here? We have analyzer with just struct with post-process, and then we have implemented on the analyzer function called process, which does something, who knows, and a public function, pipeline, takes reference to self and a number. Right, let n equal self.process n. Alright, so it'll run process, put in the n, take n, and then return self.postprocess and n. I don't know the syntax. What is this? I've forgotten what the syntax means when we have. I don't remember that at all. What does that mean? Do you remember that at all? Having two bracketed spaces in a return? I guess it's not really meaningful. I believe that this is fn once, honestly. Huh. I can't even think what that would do. We have two bracketed pieces. It's passing back from pipeline, which just puts back an I32. Post-process is something of type F. Okay. So I guess by that definition, fn mute would make the most sense, yeah? Does this mean that it passes back n, but also separately sets post-process to n? Really, I've not seen that syntax. Whatever it is, I'm going to ignore it. Oh, we got 2 out of 4 correct. Alright, let's just straight out see the questions, answers. The program does not compile. Mutably borrows s between its definition and use, so the print line, a read of s, is invalid. Okay, yeah, I was correct the first time, since it mutably borrows s, which cannot implement the borrow trait, or sorry, the copy trait, or does not implement the copy trait. It cannot be read at a later time. I guess because it could be anything at that point in time? Still, though. I guess that could have like a use after free error. I can't remember what error would come about in this, but I can understand why. Determine why the program... Yeah, we said it does compile. Because it borrows. Because it's not... Sorry, because this is a mutable borrow? No, this is a mutable borrow. I can't remember why. Because sorry, it does not capture S. Yeah, because it's passed in. Yeah, it doesn't capture S yet. S is only passed in at this point. Okay, yeah, that does make sense. So within the closure, it's not actually capturing it. It's not saying, hey, this is mine, until you actually pass it in. This is using shadowing, I see. You can make S anything, and then still pass in a mutable reference to S. So, yeah, okay. That makes more sense than what I was thinking. Alright, so just to pound this into my head, this is just creating a full-on function, and as long as you utilize the piece in here, you're not taking anything from the outside world. Here, however, you're taking something from the outside world. You're taking it into this section for as long as this section exists. And I believe this also means that you could delete. Yeah, because of the garbage can closure. I remember that. Because of the toilet can closure. You could just use that to delete some trash. Okay. Now we did get this wrong and the other one too. Nope, we got this one correct. fn mute. Oh, we got the last one wrong? The correct one is fn. Okay, so we got this one correct with fn mute. F is called multiple times, so fn once is not appropriate. Both fn and fn mute can work, and fn mute is less restrictive, so fn mute is more appropriate. Okay. Yeah, so I guess this does... Oh, yeah, this does have a type T. Yeah, I was kind of wrong about that. Self is mutable. What do you mean? There's no self in here. In the last question? So this cannot be true because self isn't... Oh, immutable. Self is immutable. That's a good point, yes. Oh, yeah, a mutable reference to something of type T. Whereas self is immutable. You cannot change self, of course. That would be idiotic if you could. Cause a lot of issues. So it can't be fn mute because part of it, or sorry, the first part of it is immutable. Okay. Pipeline could be called multiple times, so fn once is not appropriate. Pipeline takes an immutable reference to self. If f were fn mute, it could not be called within pipeline. Therefore, fn is the most appropriate here. Okay, so the only way we're going to be having fn is in the circumstance, is in some very specific circumstances. Fn is only the thing, sorry, the only reason you would use Fn is because the other two would be inappropriate. Fn mute is the thing you're always going to utilize if you use something more than once, and can utilize it. Whereas Fn once is only for singletons, I believe? That is my current understanding. Okay. Oh, I think we did relatively well there. 50% is a passing grade in my country, so hell yeah. Alright, now we're going to learn iterators. Iterators are probably going to be a hell of a lot easier to understand, grasp your head around. There's only 3 questions at the end of this, so hey. Processing a series of items with iterators. The iterator pattern allows you to perform some tasks on a sequence of items in turn. An iterator is responsible for the logic of iterating over each item and determining when the sequence has finished. When you use iterators, you don't have to re-implement that logic yourself. In Rust, iterators are lazy, meaning they have no effect until you call methods that consume the iterator and use it up. For example, the code in listing 1310 creates an iterator over the items in vector v1 by calling the iter method, defined on vector t. This code, by itself, doesn't do anything useful. So we just have a vector, and then we create an iterator with v1.iter. I'm assuming the .iter method will be on basically any collection, or any. I don't see why any collection would not have it. Any of the base questions likely have, or base, I just said the word. That doesn't matter. The iterator is stored in the v1 iter variable. Once we've created an iterator, we can use it in a variety of ways. In listing 35 in chapter 3, we iterated over an array using a for loop to execute some code on each of its items. Under the hood, this implicitly creates and then consumed an iterator. But we glossed over how exactly that works until now. In the example in listing 1311, we separate the creation of the iterator from the use of the iterator in the for loop. When the for loop is called using the iterator in v1 underscore iter, each element in the iterator is used in one iteration of the loop, which prints out each value. Let v1 equal a vector holding 1, 2, 3. Let v1 iter equal v1.iter. For value in v1 iter, println got, and then the value. In languages that don't have iterators provided by the standard libraries, you would likely write the same functionality by starting a variable at index 0, using that variable to index into the vector to get a value, and incrementing the variable value in a loop until it reaches the total number of items in that vector. Iterators handle all of that logic for you, cutting down on repetitive code you could potentially mess up. Iterators give you more flexibility to use the same logic with many different kinds of sequences, not just data structures you can index into, like vectors. Let's examine how iterators do that. The iterator trait and the next method. All iterators implement a trait called iterator that is defined in the standard library. The definition of the trait looks like this, right? So we have a public trait iterator, creating a type called item. We have a function, next, which takes a mutable reference to self and returns an option holding in self item, which is the type item. Methods that default implementation elided. I don't know what that means, to be honest. I don't care enough. No, you know what I kind of do. Let's see what this is. Elided? Is this a word? Elision. Ah! In linguistics, an elision or a deletion is the omission of deletion. I'm an idiot. is the omission of one or more sounds, such as vowel or consonant or variable in a word or phrase. However, these terms are also used to refer to more narrowly to cases where two words are run together by the omission of a final sound. Okay, so I don't sure. Okay, so elided just means that there are more methods after this. Methods with default implementations exist after this, but they have been elided. They have been concatenated, taken out for brevity. That is incredibly stupid. Nobody has ever used this word in regular conversation except for people who are full of themselves. Why? They just want to think, they want us to think they're cool. That's it. I don't see why they're using these words. Elision, elided, no. Notice this definition uses some new syntax, type item, and self item, which are defining an associated type with this trait. We'll talk about associated types in depth in chapter 19, quite a while away. For now, all you need to know is that this code says implementing the iterator trait requires that you also define an item type. And this item type is used in the return type of the next method. Hell yeah. Elided! Yes, money! Fucking hell. In other words, the item type will be the type returned from the iterator. The iterator trait only requires implementers to define one method, the next method, which returns one item of the iterator at a time, wrapped in sum, and when iteration is over, returns none. You can call the next method on iterators directly. Listing 1312 demonstrates what values are returned from repeated calls to next on the iterator created from the vector. Alright, so we get a test function, iterator demonstration, we get a vector, 1, 2, 3, that we've created an iterator here. Alright, so we assert equality that v1 iterator next returns exactly a sum variable with a reference to 1 in it, the number. And these, I assume, are true. Right? So every single time you hit next, it'll paste out the current index and then iterate to the next one. You'll get all of this until you get the none field, the none option. Makes sense. Note that we needed to make v1 iter mutable. Yes, because it mutates, it changes. You can't have an immutable iterator. It'll change value. Calling the next method on an iterator changes the internal state of that iterator. Changes the internal state that the iterator uses to keep track of where it is in the sequence. In other words, this code consumes or uses up the iterator. Each call to next eats up an item from the iterator. We don't need to make v1 iter mutable when we used a for loop because the loop took ownership of v1 iter and made it mutable behind the scenes. Okay? That's fairly confusing. So an immutable object gets copied and then overshadowed behind the scenes, or does it just say, no, you're now mutable, I wonder? I don't think it really matters. In the end, in the for loop, does it consume fully the iterator? In a for loop, does that mean v1 iter would be destroyed and no longer usable? These are questions I won't answer. Also note that the value we get from the calls to next are immutable references to the values in the vector. The iter method produces an iterator over immutable references. If we want to create an iterator that takes ownership of v1 and returns own values, we can call into iter instead of iter. Similarly, if we want to iterate over mutable references, we can call iter mute instead of iter. Okay. That's quite good to know. So by default, it is still immutable. Even if you have a mutable variable, you are simply mutating the iterator. However, if you want a mutable section, you do an iter mute. Sorry, if we want to create an iterator that takes ownership of v1 and returns own values, we can call into iter. Okay. Yeah, so the original iter is just if we want the value, which we are copying over and utilizing elsewhere. Into iter is if we want owned values, which would be, I believe, references directly to the original immutable data, instead of iter, meaning that at the end it'll be destroyed. If we bring it into a scope, it'll be destroyed at the end of that scope, I believe, if it takes ownership. And then thirdly, we have iter mute, which will take a mutable reference, or probably, a mutable reference, meaning it is borrowed, to whatever data was originally in the v1, the vector. Okay. Methods that consume the iterator. The iterator trait has a number of different methods with default implementations provided by the standard library. You can find out about these methods by looking into the standard library API documentation for the iterator trait. Some of these methods call the next method in their definition, which is why you're required to implement the next method when implementing the iterator trait. Methods that call next are called consuming adapters, because calling them uses up the iterator. One example is the sum method, which takes ownership of the iterator and iterates through the items by repeatedly calling next, thus consuming the iterator. As it iterates through, it adds each item into a running total and returns the total when iteration is complete. Listing 1313 has a test illustrating the use of the sum method. Alright, so we got a bunch of stuff you want to add up. You create an iterator out of it. You say, hey, this total will equal sum of everything within this vector. 1 plus 2 plus 3 is 6. Assert equal will be true. We aren't allowed to use v1 iter after the call to sum because sum takes ownership of the iterator we call on. Okay? Right, let's just read that again because I'm tired and can't really read correctly. We aren't allowed to use v1 iterator after the call to sum because sum takes ownership of the iterator we call on. Okay, yeah, so since this takes ownership, at the end of this, the iterator is essentially destroyed, so we could not utilize the iterator again to get, like, the third value. Or to, do any other math on it. We'd have to create a new iterator off of v1. Does this mean that ownership of v1... Well, ownership of v1 was never taken, I don't believe. Iterator adapters... Oh, yes. Methods that produce other iterators. Iterator adapters are methods defined on the iterator trait that don't consume the iterator. Instead, they produce different iterators by changing some aspect of the original iterator. Listing 1314 shows an example of calling the iterator adapted method map, which takes a closure to call on each item as the items are iterated through. The map method returns a new iterator that produces the modified items. The closure here creates a new iterator in which each item from the vector will be incremented by 1. Right? So we simply create an iterator off of vec1, 2, 3. We then call .map on the resultant. Inside of here, we simply have a closure, which takes in x being passed in from v1.iter and outputs x plus 1. Simply adds 1 to this, so that'll be 2, 3, 4. However, it'll produce a warning. Okay. Unused map that must be used? Huh. Note, iterators are lazy and do nothing unless consumed. Oh, because this returns an iterator. Okay, yeah, so in order to have this work done, you actually have to iterate through the thing that's passed out. Okay. Yeah, I wouldn't have caught that. In JavaScript, map would just work on v1. Yeah, that would just work on v1. So yeah, this will pass back, so you'd have to have let map it equals and then this, and then you'd have to iterate through it via a loop. Warning iterators, bin iterators, generate 1 warning. Alright, yep, that's fine. The code in listing 1314 doesn't do anything. A closure we specified never gets called. The warning reminds us why. Iterator adapters are lazy, and we need to consume the iterator here. To fix this warning and consume the iterator, we'll use the collect method. Oh, which we used in chapter 12 with env args. Listing 12-1. You get a similar error when benchmarking? Oh, damn. Always one day off. And you're always ahead of me. That's okay. I got somebody to lean on. It's weird how this goes 13 chapters in before we get to some of the more useful features of this. Like, iterators are very common in Rust. It's weird how we have to get this far, and how many hours have we progressed in this? I'm really curious. I have a log of it, which is a great thing. I'm going to look into this later to see how long we've been reading this dang book before we got to just iterators. My lord. Right, to fix this warning, yep. So collect just turns it into a vector. In listing 1315, we collect the results of iterating over the iterator that's returned from the call to map into a vector. This vector will end up containing each item from the original vector incremented by 1. I'm assuming this is just a for loop of some kind inside. Let v1 equal vec by 32. 1, 2, 3. v2 is a vector, which just utilizes the map, collects the map, and passes it into v2. Assert equal v2, 2, 3, 4. Yep, these will be the same. There's so many fuck guns in this language, seriously. Just an immense amount, honestly. I'm surprised anybody who writes Rust can actually walk it anymore. Maybe that's why they write so much Rust, they're stuck at their desk. Calling the map method to create a new iterator, and then calling the collect method to consume the new iterator and create a vector. Because map takes a closure, we can specify any operation we want to perform on each item. This is a great example of how closures let you customize some behavior while reusing the iteration behavior that the iterator tree provides. You can chain multiple calls to iterator adapters to perform complex actions in a readable way. But because all iterators are lazy, you have to call one of the consuming adapter methods to get results from calls to iterator adapters. Using closures that capture their environment. Many iterator adapters take closures as argument, and commonly the closures we'll specify as arguments to iterator adapters will be closures that capture their environment. For this example, we'll use the filter method that takes a closure. The closure gets an item from the iterator and returns a bool. If the closure returns true, the value will be included in the iteration produced by filter. If the closure returns false, value won't be included. In listing 1316, we use filter with a closure that captures the shoe size variable from its environment to iterate over a collection of shoe struct instances. It will return only shoes that are the specified size. Simple struct, shoe with a size and style. Function, shoe and size, takes in shoes vector, shoe size, and returns a shoe, a vector of shoes. Right, so we take shoes, which is passed in as a vector of shoes, dot into iterator, creates an owned, right, so this creates an iterator of owned objects, I believe. Is that what it is again? Let's double check. Oh, I can't make marks again. Let's take this and just check. If we want to create an iterator that takes ownership of v1 and returns owned values, we can call into iterator instead of iter. Yes, it does. Okay. Apologies for that, just wanted to make sure I'm not giving my brain false info. Filter takes in s, meaning it doesn't capture the environment. s.shoesize equals shoesize dot collect. I thought this was supposed to capture the environment. This won't. I'm guessing that we do that later. Anyway. Alright, so we have useeker, we have a test, we have shoes, a bunch of shoes. Let in my size equals shoe in my size, shoes 10. So now we have in my size. Alright, we have assert equal and it'll be that vector. Huh. The shoe and size function takes ownership of the vector of shoes and a shoe size as parameters. It returns a vector containing only shoes of that specified size. In the body of shoes and size, we call into_iter to create an iterator that takes ownership of the vector. Then we call filter to adapt the iterator into a new iterator that only contains elements for which the closure returns true. The closure captures the shoe size parameter from the environment. It does it? Oh, it does, yes, right here. I was focused on this. It does in fact capture shoe size, that is correct. Alright, takes ownership, it returns a vector, in the body we call iterator, create the filter, close true. Alright. Captures the shoe size parameter from the environment and compares the value with each shoe's size, keeping only shoes of the size specified. Finally, calling collect gathers the values returned by the adapter iterator into a vector that is returned by the function. The test shows that when we call shoes in size, we get back only shoes that have the same size as the value specified. And now we have a quiz. Fantastic. Alright. Which of the following best describes why iterators are lazy? So it's lazy because it doesn't do anything until called. An iterator will only iterate over a given number of items. That is incorrect. An iterator takes ownership and sequences of items that are iterating over. Nope. An iterator creates a copy of each item. That is incorrect. Has no effect until you call a method that will extract elements from the iterator. Fantastic. Yep. Good shit. Probably got that at the same time with a delay, I believe, right? I don't know how much she's delayed. Now you probably got it before me. True or false? There's two code snippets that are these are semantically equivalent. I'm quite alright. So we have a while loop. Let sum, which is an option x equal iter.next. Well, let and then we just iterate versus for x in iterator. Then we run function x. Yeah, I believe these are semantically the same. A while let will do something. Well, this is true. Sorry, well, a condition is true while also creating a variable with the output of the equal. And when, as long as this is an option that has sum within it. I think I understand this well personally, but I am not describing it well. I believe that these are semantically, that though they are semantically equivalent? Whatever. Yep, these are the same thing. Determine whether the program will pass the compiler. If it passes, write the expected output of the program as if it were executed. Right, we have a vector, 1, 2, 3, 4. Let A equal a vector without a type. v.iterator filter. We have a reference to an I32. We dereference x, which is a reference, divided by 2. I don't care. This is I don't care. Alright, I guess I do have to care. Let's actually read this. Alright, so we create an iterator, we filter over it with this section. We have alright, so we bring in ref is normal? Yep, ref is a normal thing. That's just a reference to a reference. So we are taking a reference to the pointer. We're creating a pointer and then we're getting a pointer to said pointer. Then we are dereferencing down to the pointer modulo 2 equals 0. If the value is divisible, if the value is divisible by itself, even I don't care. I can't remember what mod 2 is. Yeah, if there's no remainder over division of 2, so if it can be divided by 2 normally, if it is even, allow it to be in, so that would be 2 and 4 would be placed in, and then we would write this function over it, which takes in x, which is a reference to an I32, which will be 2 and 4, then x times 2 would be 4 and 8, and then we have 4 and 8 within A. I've probably missed something and have fucked something up, but I believe this is the current path of things. Let B equal a vector v.iter.map, taking in x, which is an I32, a reference to an I32, x times 2. Let's just check on this. Alright, so that's v, I believe. Can you utilize v twice in the same way? Since this is just iter, it's a non-owning. I don't believe that iter will own this at all, so I believe that this is fine. Utilizing v twice, I believe, is fine because it is a non-owned. It doesn't own v. Not even borrowing, I don't think. Right, I believe this is fine. And collect will simply place it into a new vector, I believe. I believe that is a new vector. This isn't actually mutating the immutable variable. Yeah, that can't be mutating, so yeah, I guess it's fine. Right, so we're taking in a reference to an I32 and multiplied by 2, filtering out anything that is not even. Alright, dot filter, taking in x, which is passed in, which is a reference to an I32. X modulus of 2 equals 0. So that's the same shit. This is just 2 full. And then we print A0 and B0. A0 will be 4, B0 will be 2. Personally, I don't directly see anything that is at issue. I think this is fine. I don't personally see any issue at all. Let's just quickly skim over this. We got a regular filter, that is fine. We are not capturing anything from our output, it's just simply being pushed in. Dot map is simply taking in x again, which is a resultant of this filter command, which is simply dereferencing x modulos O2, making sure it's everything that's even, and we're simply collecting it. We aren't trying to mutate v, I don't believe. I think this is fine. And if it does compile, that will be 2 space 4. Right, unless you disagree, I'm just going to click submit. Yeah, I don't see any problem. I want to see a problem with this. This is the issue. I always want to see a problem. When I see no problem, it makes me question myself. And often I am right to question myself, but you know. Alright, I think that 2-4 is correct. Let's see. Ah, got something wrong. Which one was it? The end one. What? Oh! I got the wrong output? Oh, it's 4-2! Oh my god, I'm an idiot. It's 4-2. Not 2-4. Wow. Ah, she happens, you know? I'm not worried about it. I had the right idea at one point, and then I messed it up. But you know, that's why we have computers. 4-2. Yeah. Yeah. I feel sad about that. But you know, in my heart, in my soul, I got 3 out of 3. That doesn't count. That's not actually counting. But you know, it makes me happy to pretend. Right, correct. An iterator has no effect until you call a method that extracts the element from said iterator. Right, context. Lazy generally means does not work until asked, and iterators do not perform any computation until iterator next is called. That's going to mess me up. Not too much, actually, now that I think about it. Well, on map it will, but you know. I'll just try and remember everything's immutable by default, and map copies, it creates a new thing. True, false. Equivalent, these things are equivalent. This is true. The for loop is syntactical sugar, or well lit, which is itself a sugar for loop and break. Oh, sorry, for regular loop and break. Yeah. Which itself is a syntactical sugar for a go-to statement and some labels, which is itself syntactical sugar for storing references to increases and decreases in register changes over a period of time. which is itself, of course, an abstraction. Continuing. I love programming. You can go down a rabbit hole on the most stupid things. Seriously, if you go down far enough, everything's very funky. Nothing's real, everything's fake. The last thing is, we got this, I say I got this correct. I think I got this correct. You know, I'm going to pretend I did. The order of iterators matters. Programming is very sweet. It's amazing. I love how much you can learn off of the stupidest stuff. Right? It matters the iterator. Yep. Order of iterators matters. A filter and a map is not the same as a map and a filter. Oh, I didn't even notice that was what's going on. Yeah. Oh, I got this wrong. Oh, I got this wrong. Oh no, I actually did get this wrong. Oh my god. Yeah, because of syntax sugar. Look, I think the sugar's rotting my brain as well as my teeth, man. But I did get this wrong. I didn't think of this. The actual output of this is, because this is map, not filter, the actual output of this would be 2, 4, 6, 8. And who do we appreciate? Not me. I mean, the end output is the same, which is the worst thing. That is the worst thing in programming. When you get something right, but are still wrong. My god, I'm stupid. At least I look nice, you know? You might wonder why the first filter uses dereference x, and the second filter does not use dereference x. v.iter produces an iterator, item equals reference I32. The filter call takes an iterator, item equals type, as input, and passes reference type to its predicate. Therefore, x reference on line 3. I don't understand. The rest standard library implements the remainder operator moduloso for reference I32 on the left-hand side, see the doc, but not for reference I32, so we have to dereference it once to use it in the expression reference x moduloso 2. I don't understand. You might wonder, alright, I'm just going to reread this again. v.iter produces an iterator, item equals reference I32. Right, so v.iter creates here a reference to an I32. So passed here into x at every single point will be a reference to an I32. However, what as input and passes reference t to its predicate. Therefore, x. I don't understand this. Huh. It returns reference type as predicate. You know, I'm going to pretend I didn't see it. By contrast, on line 4, when .map takes an iterator item equals t as input, it passes t to its closure. Therefore, the closure in map takes reference I32 as input. The multiplication operator is implemented for reference I32. So x does not need to be dereferenced in x times 2. The operation x times 2 produces a value of type I32. So the result of the map is an iterator item I32. The filter then takes x I32, which also does not need to be referenced to do x moduloso 2. Huh. What? Okay, so the filter is an item with I32. Right, so the result of the map is an item with an I32, and thus the filter takes a reference to an I32? I don't understand why. Right, so I do understand that what it's attempting to state here is that it needs the reference to the reference of an I32 in order to pass through to the map a reference to an I-32, which is required for the next calculation instead of simply an I-32. I believe. So you need to reference it one. You know what? I don't think I'm going to get this today. I'm a bit dumb. But I'm okay with that. Right! We're going back to the input-output project. I cannot remember what that was called. I believe that it was called Minigram? Okay. We still have some time left, so absolutely we're going to go into this. Take up your text editor if you're following along at home. With this new knowledge about iterators, we can improve the I.O. project in Chapter 12 by using iterators to make places in the code cleaner and more concise. Let's look at how iterators can improve our implementation of the config build function and search function. Right, where's the build function? Well, it would be here. Wow. Good stuff, my guy. Right, where would an iterator be useful here? You're confused too? I'm thankful. I am very thankful. I don't know what that means. Like, it's probably something to do with elation and being elated, you know? I'm not elite enough, you know? Right, where are we utilizing an iterator here? Build. Result static conf. If argument's length is 3, and we let query 1 clone, perhaps we're using an iterator here to clone on each object into a new piece. So yeah. Okay, so maybe right. So here's my guess: we utilize the iterator to move tabs. I use bar, I believe. What am I using? That's a good question. What is it called? Is it not bar? I guess it's not bar. My lord. I thought it was bar. Winbar? What is this? Buffer line. I utilize a plugin called Bufferline. It's not using tabs actually, it's just using the buffers. So instead of utilizing tabs, which is an entirely different selection, which is basically the entire window, it's utilizing buffers, which is just every open file on your computer. I can still use tab new to have like an entirely new structure here with a different like zoning, different windows and stuff. But you know, I tend not to, honestly. I just like the regular tabs. And I just have it set up to leader H and leader L. But that is what I'm currently using. Heavily suggested. I can't remember what it was before. But you can look back at the mod. Quite cool thing. Bufferline is it. I really like Bufferline. It looks really nice. But you do have to add in like a few things to get it to look like that. Right, what are we doing? Removing a clone using an iterator. In listing 12.6, we add code that took a slice of string values and created an instance of the config struct by indexing into the slice and cloning the values, allowing the config struct to own those values. In listing 13.17, we've reproduced this implementation of config build function as it was in listing 12.13. Right, yep, here is the original. You know, I'm going to go forward without reading. Always a great idea. What I believe we are going to be doing is right. So I believe what we are going to do is put something like this: args.iter. Right? Maybe we want it to be owned. Who cares though? Right? It's going to be something like let arg iter equal this. At which point we are going to do some like for loop for arg in arg iter, and then we are going to create. Okay, I'm a bit lost now because how do we create config like this? We'd have to create a an empty config at this point. Let config equal no. Why would we not just collect? Yeah, we're probably going to collect it into a vector, taking out the first one, filtering out the first one, perhaps. Yeah, I guess we should probably read forward because I don't know what I'm doing. But I think I have a good idea of what we're doing here. We're probably going to be using a lot of the scope. We probably don't need this for loop, however. We're almost certainly going to be collecting it after popping. Probably just, why not just writing to next on this? Let's just do arg iter.next. Oops. What is .ne? That's a thing? Determines if the element of this iterator are not equal. Oh, not equal. Right, now that'll take out the first one, and we can just do the rest. I'm going to continue reading at this point, however, because I don't know how to take a vector and just plant that onto the first two pieces here. And then ignore case as well. Yeah, we'll probably need this. Yeah. Anyway, let's just continue reading. We need a clone here because we have a slice with string elements in the parameter args, but the build function doesn't own args. To return ownership of a config instance, we had to clone the values from the query and file path fields of the config, so the config instance can now own its values. With our new knowledge about iterators, we can change the build function to take ownership of an iterator as its arguments instead of borrowing a slice. Oh, so we're just going to be straight out changing this. We're going to have an iterator that we build into here. Alright. Yeah, I was wrong. Once config build takes ownership of the iterator and stops using indexing operations that borrow, we can move the string values from the iterator into config, rather than calling clone and making a new allocation. Alright, I am glad I did this because this shows me how little I am thinking of iterators. Currently, I'm not really thinking of iterators as a buffers and tabs. Oh, yeah, so buffer is just like a list of all files you have open, whereas tab is an entirely different thing. I mean, buffers are how you think of tabs. Like, if we just put in buffers, here's everything that we currently have open. However, tabs is like an entirely new way of an entirely new layout. As you can see, that little thing to the left no longer exists there. So if we do like v-split, we'll create like and then h-split. Wow, that's well, horizontal. Wow, I'm really good at this. I don't do horizontal splits. Sure, there we go. We have this thing which has like this, and then perhaps some entirely different thing here. And then we do tab next. We have our previous layout. Ah, that's the word I was looking for. It's essentially just a new layout. As you can see up here, we have all of our buffers as we had before. And if we go to the next, we have an entirely different layout. Really useful for this is to have like a debugging. Oops. What? Okay, so my debugging's broken currently. But if we had a debugger running currently here, we'd have debugger and all of its shit, which has like 3 different things here. But then separately, just still have our regular coding setup as we had before. You understand? Yeah? Took me a while to understand that. You're smarter than I am. My god. Yeah. Oops. Yeah, that'll happen. Ignore that. I quite like it, honestly. I really like that exists. I'm quite glad it exists. I don't use it often enough. Thank you for reminding me, honestly. Once debug, once config build takes ownership of the iterator and stops using indexing operations. Yep, you have read that. Using the returned iterator directly, open your IO project source main.rs file, which should look like this. Alright, so we simply have main. Now we're going to create an iterator over here, correct? Args collect. We probably don't need to collect if this is already an iterator. Is args an iterator? The returned iterator will panic. Alright, so it does return an iterator, but it doesn't state it very clearly. Hello. Thank you. Alright, so here is the original here. We'll first change the start of main function that we had in listing 1224 with the code in listing 1318. Which is here? Is this it? Yep. Which this time uses an iterator. This won't compile until we update config build as well. Right, so here we have changed. What exactly have we changed? Right, config build, taking in a reference to arg. Nope, that's a different thing. So we are simply taking env arg. We are simply taking that. What? I don't know what the hell just happened. What just happened? This should be working. Yes. What? Oh. Okay. No, what am I doing wrong? Sorry, I'm just I don't understand why my register is not printing. Right, so in one is eprint. Why is that there? Okay, something's broken with my printing. I don't understand why. Does not matter. We'll just pretend that I don't have access to that. Alright, that took a long time to put this inside of here. But we learned nothing, so it's well worth it. Right, and that's literally all we're doing. We have simply passed in env args to this place and deleted it, have we not? Separately, we have this unwrap or else, which will do nothing. Right, so this will unwrap or else. I don't know what that does to an iterator. I guess this is likely an option that will return an iterator, which is now within config. And if it doesn't unwrap, it'll just print out a failure. That is what we are currently doing. Yep, that is the only thing we have placed in here. That's it. That's all we've done. That's really all we've done? Yep. That's really all we've done. Okay. The env args function returns an iterator. Normally, yes. Rather than collecting the iterator values into a vector and then passing a slice to config build, we're now passing ownership of the iterator returned from env args to config build directly. Next, we need to update the definition of config build in your IO project source lib.rs file. Let's change the signature of config build to look like it does in listing 1319. This still won't compile because we need to update the function body. Right, config build, we are simply going to alter a little bit here. Right, public function build has a bunch of stuff on another line. It takes in Mutable args. Mute args. Which simply which needs to implement iterator where item equals a string. Then we are also separately taking in what? Why is there a comma there? Why is there a comma there? Is there a comma there? Yes, there's a comma there. Okay. So we have a comma here and a new line. And we return a result config or a static string with the reference left in. Right. That's it? Yeah, that's not gonna work. Oh, that's not gonna work at all. Does the comma do something in this situation? Right, let's just copy paste. This is within an implement config. Okay. I'm in the wrong place, I think. Nope, I'm in the right place. You know, let's just, again, copy all this stuff out and replace it. Is that fine? No, still not fine. This is broken. Something's broken. Oh no, I'm inside of a shift K. Sorry about that. Yeah, it just didn't show up my pretty stuff. Okay, what is going on here and why do you not work? Really? Method iter not found on this type parameter. There must be something else here. Is this... I mean, it says it's not going to compile, but it's because of the function body. Is there something missed here? No. What the fuck is going on? It must be something small that I'm just missing. I don't understand what's going on here. Is there a bug in this code? Because I don't see why this is here. I see no reason for this. That doesn't exist is probably fine, right? Still no. Absolutely not. It's still broken. Uh, mismatch type, expected enum results, static config, found type, unit type, nothing. Okay, that's fine. Currently, that's fine. If that's the only issue, it's fine. Was that the original issue that I was having? No. Maybe, actually. Maybe I'm an idiot. Nope. No method named length parameter implement iterate string in the current scope. It's a method with simple name le. Mishmash types expected. Okay, apparently this is fine. I'm just gonna assume this is fine, and I'm not reading it correctly. Oops. Wow. Really stop you. This is fun. Does this take out that error? No. Does this take out that error? No. Oh yeah, I understand why that error is how it is. Okay, so this is the same error body, but there's also... You know what? Whatever. Sorry for taking your time up. That was useless. I'm just going to continue from exactly what it states here. Standard library documentation for the env-args function shows that the type of the iterator returns a standard env-args, and that type implements the iterator trait and returns string values. We've updated the signature of the config build function, so the parameter args has a generic type, where the trait bounds impl iterator item equals string instead of reference string. This usage of the impl trait syntax we discussed in the traits as parameters section of chapter 10. This usage of the impl trait syntax we discussed in traits as parameters section of chapter 10 means that args can be any type that implements the iterator type and returns string items. Because we're taking ownership of args and will be mutating args by iterating over it, we can add the mute keyword into the specification of the args parameter to make it mutable. Yep. Because args is just an iterator, we don't need to take ownership of the underlying stuff. Using iterator trait methods instead of indexing. Next, we'll fix the body of config build. Because args implements the iterator trait, we know we can call the next method on it. Listing 1320 updates the code from listing 1223 to use the next method. Right, so first thing we do is just args.next, which is one of the thoughts I had originally too. Stuff. Args.next. Perfectly fine. Then, well, let's take this out for now. Then we simply bring this back up, changing out the let query equal, and then it's going to be a match. Been a while since we've seen our friend match. Args.next. Matching against the next structure, we are going to say if there's some, calling the value arg, return. That's not what I want. Yes, it is, I guess. Arg. Just return arg. Great stuff. None. Capitalization. You want to return? Error. Capitalization. Failed to get period string. Nope. That needs this comma. Here needs a semicolon. Alright, next we do the same thing with file path. What? File path. File path is args.next, sum arg, elsewise file path. Fail to get the file path. Right? Next, we still have the original thing. I think I deleted it. Ignore equals, yep, that's still the same thing. And this is still the same. Yep. Okay. That's all we're doing. So all we have done is we created two new match statements if something exists within that path. Sorry, within that argument, we return arguments to file path. Elsewise, if it's none, we return an error failed to get file path, which will be the value for file path. Yeah. Then okay is simply all these three things. First off, we do take args.next to delete that first bit, which is just the path, the original. You were just adding plugins and stuff? Hey, good stuff. I'm glad that you didn't see me fail horrifically a few times there. You know, it always makes me happy to know my failures aren't being watched. Not an issue. All we really did here was change stuff over to use match patterns. Just returning the next value from args.next and taking out the first one, just popping it out, then passing it all back into OK as we had before. I wonder if we could just... I'm really curious if we could just take this out, paste it here, then just have this here? Yeah, could we not? Why would we not be able to? What are the errors that it's stating? I've forgotten how these things work. Does that work? Yeah. Yeah, that works! Yeah, that works. I like this syntax better. I'm going to change it over to my own detriment. This is not going to be helpful. In fact, this is going to be bad because we are diverging. I do not suggest anybody else diverge randomly from what has been placed before you. This is not a good idea. This is how I'd likely write it myself. I will keep ignore case because this is actually doing some nice work. But this is what I'd do if I was on my own. Yeah, so that's good. We can just use the match directly in here. Set it to the value of the query. Which seems to be what we were doing before. I don't see an issue with this. It'll come back to bite me in the ass soon, though. Making code clear with iterator adapters. You can also take advantage of iterators in the search function with our IO project, which is reproduced here in listing 1321 as it was in listing 1219. Alright, so let's search for the search function. Public function search. Alright, this is for a line in contents.line. What does contents.line pass through? Isn't it an iterator? Yep. This passes in an iterator. I think we're literally just using that, aren't we? Are we not utilizing an iterator already? Doesn't matter. We'll find out. We can write this code in a more... Oh, yeah, because we're utilizing... Oh, yeah. Why do we need the for loop at all? I see. Here's what I'm going to guess is happening. You've been getting a lot of that today. Probably just going to collect. Right? This is just a vector. Why not do this? No. Oh. Query's not being used. Oops. Oh, no, yeah, we need... I'm a fool. Right. So we need dot filter with the predicate. Predicate will be... I can't remember how to use filter. Filter, I believe, takes in... Nah, we don't really need to... We can capture, can't we? We'll just capture filter. Oh, yes, I remember. Line. Line equals exactly filter. Or line dot contains... Sorry. Line dot contains query. This is my assumption. This is my prediction on what the function is going to look like in the end. Takes x if whatever function applies to x returns true. Yeah. Thank you for that. Yeah, I think that this will work. Yeah, it's passing back a vector in the end. My LSP thinks it'll work. That's a nice little one-liner if it works, but hey, I don't know. We can write this code in a more concise way using iterator adapter methods. Doing so also lets us avoid having mutable intermediate results vector. Having a mutable intermediate results vector. Yep, I got that deleted too. The functional programming style prefers to minimize the amount of mutable state to make code cleaner. Removing the mutable state might enable a future enhancement to make search happen in parallel, because we wouldn't have to manage concurrent access to the results vector. Listing 1322 shows the change. Alright, we have contents, .lines, .filter, line.contains query, and then collect. You know, the difference between mine and theirs is that theirs is on different lines, and I hate that syntax. It makes me sad. Yeah, that works fine. I'm fairly proud of myself for doing a very basic thing. Fantastic. Recall that the purpose of the search function is to return all lines in contents that contain the query, similar to the filter example in listing 1316. This code uses the filter adapter to keep only the lines that line.contains query returns truthful. We then collect the matching lines into another vector with collect. Much simpler. Feel free to make the same change. Use iterator methods in the search case insensitive function as well. Oh yeah, we're just doing two lower, right? I don't feel free to do that, honestly. I feel like I'm quite bound to not do out of laziness. Choosing between loops or iterators. The next logical question is which style you should choose in your own code. If you have more than a few lines on you should absolutely utilize a loop. If you want specific scope, you should absolutely utilize a loop. If you have a simple one-liner, you should absolutely use an iterator. Oh, sorry, I'm thinking of like on map or filter. If there's a lot of logic, though, you should also use a loop. And why? The original implementation 1321, or the version using iterators in listing 1322. Most Rust programmers prefer to use the iterator style because it's better. It's a bit tougher to get the hang of at first, but once you get a feel for the various iterator adapters and what they do, iterators can be easier to understand. Instead of fiddling with the various bits of looping and building new vectors, the code focuses on the high-level objective of the loop. This abstracts away some of the commonplace code, so it's easier to see the concepts that are unique to this code, such as the filtering condition each element in the iterator must pass. But are the two implementations truly equivalent? The intuitive assumption might be the more low-level loop will be faster. Let's talk about performance. I don't know about that. It really depends on your use case. I mean, there's a bunch of structure built in with the within map or the other one, within map or filter. However, that also allows for more performance with a lot of unsafe code or specific code relevant to it instead of just hoping the compiler understands something. There's a lot more opportunity for Rust to be doing more things under the book. Comparing performance, loops versus iterators. Right, so we got a little bit of time left, but this is rather small. This will likely be the last thing we read today. Which is good, because it's the last thing before more about Crace on Crace.io. Which will be a very quick... Smart point! No, don't tell me that they have fucking smart pointers. Oh, no. I hate C++. Why is Rust C++? Alright, let's not judge it till we get there. Comparing performance, loops versus iterators. To determine whether to use loops or iterators, we need to know which implementation is faster. No, we don't. Who cares about speed in this day and age? The version of the search function with an explicit for loop or the version with iterators? We ran a benchmark by loading the entire contents of The Adventures of Sherlock Holmes by Sir Arthur Conan Doyle into a search and looking for the word "the" in the contents. Here are the results of the benchmarks of the version search using the for loop and the version using iterators. You don't know what smart pointers are, but you're scared you should be. Unless they've changed the hell out of it, smart pointers are a train wreck waiting to happen. Well, they're a singular train in a large project. If there's any other train, they're built on different tracks and they're eventually going to collide. You need to utilize one structure only, and not care about whether or not it's correct for the specific point that you're utilizing. Smart pointers are horrible. I'm not going to be able to explain why without explaining the entirety of like C++, because I'm not that learned on C++, I guess, but just they're one of the main reasons I hate C++. Maybe Rust does it better. Everybody says Rust is just better C++. That's quicker and more like C, so maybe it's better. Right, I don't know what this means. Okay. For versus iter. 90,000. Right, this amount ns per iter? Plus or minus that amount? I don't know what that amount means. The iterator version was slightly faster. We won't explain the benchmark code here, because the point is not to prove that the two versions are equivalent, but to get a general sense of how these two implementations compare performance-wise. For a more comprehensive benchmark, you should check using various texts of various sizes as the contents, different words and words of different lengths as the query, and all other kinds of variation. The point is this: iterators, although a high level of abstraction, get compiled down to roughly the same code as you've written in a lower level code yourself. Yeah, it's just syntax sugar, I guess, if it's roughly the same code. Iterators are one of Rust's zero-cost abstractions, by which we mean using the abstraction imposes no additional runtime overhead. This is analogous to how Bjorn Stroustrup, the original designer and implementer of C++, defines zero overhead in Foundations of C++. By the way, though I hate his language, incredibly intelligent human being. Seriously, reading his work is something I suggest any programmer do, even if you disagree with him in a lot of ways. He probably agrees with you in a lot of ways too. I think he hates C++ as well. He just won't tell you that. In general, C++ implementations obey the zero overhead principle. What you don't use, you don't pay for. And further, what you do use, you couldn't hand code any better. Oh, you couldn't hand code any better. As another example, the following code is taken from an audio decoder. The decoding algorithm uses the linear prediction mathematical operation to estimate future values based on a linear function of the previous samples. This code uses an iterator chain to do some math on three variables in scope: a buffer slice of data, an array of 12 coefficients, and an amount by which to shift data in ULP shift. We've declared the variables within this example, but not given them any values. Although this code doesn't have much meaning outside of its context, it's still a concise, real-world example of how Rust translates high-level ideas to low-level code. Right, so we got mutable I32, a 12 I64s, and one I16. For 1 in 12 to buffer.length, let prediction coefficient iter.zip.map. I don't know what zip does. Well, we got some code here. Why not just check what zip does? This will give us an iterator. Zip zips up two iterators into a single iterator of pairs. Turns a new iterator that will iterate over two other iterators, returning a tuple where the first element comes from the first iterator and the second element comes from the second iterator. Okay, that's kind of cool. So turns two iterators into like a key value pair. Taking in a reference to buffer I minus 12 all the way to I being 12, 13, 14, 12, 13, 14, 15, so on and so forth. And then it creates a pair of those, because I guess buffer is mutable list of I32s? I don't understand. You know what? I don't think I'm supposed to understand this, because it's going to explain it here. To calculate the value prediction, this code iterates through each of the 12 values in coefficients and uses the zip method to pair the coefficient values with the previous 12 values in buffer. Oh yes, this takes coefficient.iter, so that's where the original comes from. So it'll take all of the coefficients and pair it with an element within buffer. Okay. Why is I 13? I don't know. Then, for each pair, we multiply the values together, sum the results, and shift the bits in the sum. You'll be shift bits to the right. Okay? Calculations in applications like audio decoders often prioritize performance most highly. Here, we're creating an iterator, using two adapters, and then consuming the value. What assembly code would this Rust code compile to? Well, as of writing, it compiles down to the same assembly you'd write by hand. There's no loop at all corresponding to the iteration that took iteration over values and coefficients. Rust knows that there are 12 iterators, so it unrolls the loop. Unrolling is an optimization that removes overhead of the loop, controlling code, and instead generates repetitive code for each iteration of the loop. Most languages will do this. All of the coefficients get stored in registers, which means accessing the values is very fast. There are no bounds checks in the array access at runtime. Aren't there? You have I64s, I32s, and I16s. Unless you're sorting those specifically while creating some logic to accept those values with, which I guess is likely what it's doing. You'd have to have bounds checks. Oh, specifically on the array accesses. Yeah, there wouldn't be. All these optimizations that Rust is able to apply makes the resulting code extremely efficient. Now that you know this, you can use iterators and closures without fear. They make code seem like it's higher level, but don't impose a runtime performance penalty for doing so. Yeah, that's really good. Summary. Closures and iterators are Rust features inspired by functional programming language ideas. They contribute to Rust capabilities to clearly express high-level ideas at low-level performance. The implementations of closures and iterators are such that runtime performance is not affected. This is part of Rust's goal to strive to provide zero-cost abstractions. Now we've improved the expressiveness of our I.O. project, let's take a look at some more features of Cargo that'll help us share the project with the world. Okay? Next time, on the Rust programming language, we'll be learning about Cargo and Cargo crates, specifically customizing build. I guess at this point, you've learned enough that we are confident you could publish something to Cargo and crates that could be of some value. And honestly, I agree. We are currently where? 14 out of 22. That's just the appendix. We are nearing completion. Seriously. Soon enough, we're going to be finished this, and honestly, I'm kind of sad about that. That's a bit saddening. Something I've been doing every week, except for the weeks I haven't, for quite a while now. About a month and a half, maybe two. We'll be over. We're more than halfway done, though. And some of this we'll never use, like object-oriented programming features of Rust. That's not going to be used here. We don't need that. Still, though, thank you for joining me again, Sorbet. Absolutely. I think we should move on to trying to document the Blemming code. I think that's what we should do. I might be doing a little bit of advent of code just to flex my programming, but this might free up some time to actually start working on Lemmy. It's very hard for me to get this 2-hour period of time in my schedule, but I have been able to, so if I can keep going forward and actually start writing on this, I think that would be great. Yeah, I mean, that was the original idea. After that, I can finally help on Cliff. I feel awful for leaving that as I have. Right, anyway, thank you so much for coming in with me. I'm excited for what comes next, but I think I'm going to leave you now. I hope you have a great week, and I'll see you next week if I don't see you before then. Goodbye? Why won't you stop streaming? Hello? It's not letting me go. I'm not allowed to leave you. Oh no?